John, can you verify to me that you can see OneNote?
Yes, I can see OneNote.
Awesome, thank you. Alrighty. Okay, we're gonna go ahead and get started. And for starters, I wanted to apologize for everybody for last week. Somehow I got very confused in my schedule. And I meant to have lecture here, um, but got thrown off with the last few weeks, especially with the football game. And I have a seminar half an hour before this, so my personal apology to you guys. That was really not cool on my part. But here today, so hopefully we can make up for that. I believe this will be the second to last lecture that we have that will be recorded live. And this will probably be the last in-person lecture, I suspect. What's going to end up happening is now we're going to start transitioning to our focus on Cplex programming, and this is part of it. But with that, the most of the content will be based on how do we actually program things in Cplex. And really, we're going to be doing this in support of your guys' project. So, or I don't want to call it a project. Think of it more of a extended homework. Okay, so again, and for this extended homework, um, everybody's a little bit different. There are some people who can do this assignment within a week or two. Others of you will take the full month and you will struggle your whole way through. Um, and so I want to encourage you to, once I post it, which should be within the next few days, probably early next week, is to begin right away. Okay. Um, if if you sort of understand Cplex and what's going on, and you understand what's going on in lecture, then you'll be fine. It really isn't that challenging. But if you struggle with Cplex, then starting at the week before is probably the worst possible idea. Okay, so yeah, let's go with that. But so far, I'm pretty happy with the way people are doing. I've looked through some of the exams and people did quite well. I'm excited that this year I will get to hand out lots and lots of A's. So that always makes me happy. Okay, so with that, I'm gonna go ahead and get started unless there's any questions about the next month. So again, we got like one more lecture, I think, maybe one and a half. Everything else will be sort of recorded videos, and the focus will be on the project. Okay, so what we're gonna be talking about today is how do we translate convex optimization problems to Cplex? Last week, we had learned how we could introduce different types of convex functions as part of an optimization. So in particular, let's say we are talking about minimizing some function f of x subject to some constraints. And, we might have some linear constraints in there, but we also might have some other constraints like L1 norm, being less than some value, or an L2 norm, or even infinity norm being less than some value. And the question becomes, well, I told you that if we have convex problems that we can in fact optimize them, that they're relatively easy to do it. But how do we write these in Cplex? How do we implement in Cplex? Now, at this point, we're going to be sort of talking about the mathematical translation, okay? And again, the videos that I'm going to post on Cplex will talk more about the actual implementation, right? So like, how do you program it in? Here, we're just talking about, all right, let's get it into a mathematical structure that will allow us to program it in. And so in order to do that, we have to be aware of a couple things. So Cplex does not understand what a norm is, okay? And I'll just put understand in quotes. So if I were to try to write in, well, there'd be no way of writing this in Cplex. All right, so we couldn't take the L1 norm of X and make sure it's less than C. Cplex doesn't know how to do this, but that said, we can actually represent these L1 norms and L infinity norms and L2 norms in a way that Cplex can understand. And so what we're going to be focusing on today is what is that translation, that intermediary step, in order to get it into a linear form, okay? And this is kind of interesting because one of the things that we said was that these were in fact nonlinear. So how do we go from something that I told you is nonlinear to linear? So we're going to learn a few little tricks in order to make that happen. And so we're going to start by focusing in on the constraints here, right? And how do we linearize these constraints? And then we're going to focus in on the cost equation, and we'll discuss how do we linearize nonlinear cost equations. Now, some of these linearizations will be exact, right? So when we talk about linearizing, we'll say the objective functions and constraints. Our goal, as much as possible, is to have an exact linearization or an exact representation. And what we mean by that is that when we convert the L1 norm into a set of linear equations, they are equal at all points of X. All right? Now, in some other cases, we'll have to make do with a linear approximation. Right? And when we do that linear approximation, we're not always going to have the exact value that we want. So, so with that, let's sort of jump into how we can do this. All right, so the first thing that we're going to talk about is the L infinity constraint. Okay. All right. So what are we talking about here? All right, so we're going to start off with this idea that we're going to have some minimization f of x subject to the infinity norm of x is less than some value d. Now, we can have some other constraints. All right, so we can have ax is less than or equal to b, but these, we already know how to handle this and to program these in Cplex. Right? So what we're really focused on is this equation here. All right. So for starters, let's sort of recall what this infinity norm is equal to. Right? So the infinity norm of some vector x is given by the maximum value of the absolute value of each of the components. So if x has n dimensions, we're going to take the absolute value of each one of those dimensions and then select the maximum value. Okay, and whatever the largest value is, So whatever that largest value is, we want it to be less than or equal to D. So in fact, so I'm just going to sort these. So let's say, and here we're going to talk about when I see this, when I put this bracket, this is a sorting index from smallest to largest, okay? So it doesn't necessarily correspond to the index of the decision variable, okay? This is the smallest value second smallest value third smallest, right? So we're just going to continue this pattern. And this is going to go on all the way to x of n, which is the largest value. Okay. Now it makes sense that if we want our largest value to be less than d, right, then we can just say, well, all of these, you know, the smallest value, second smallest value, third smallest value, all the way up to the largest value, well, each one of these has to be less than or equal to d, okay? Now, we can take this one step further, right? So let's take this idea, and we can represent it by a set of equations. So what that means is, well, obviously the smallest value based on this inequality chain has to be less than or equal to d, the absolute value. Likewise, the second smallest value has to be less than or equal to d. Right? Third smallest, all the way up to the largest. Now, every single one of these is less than or equal to d, right? So this statement here is equivalent to saying, well, the infinity norm of x is less than or equal to d. Not only that, because we're going through every single index, we can drop this idea of which one's the smallest value or the largest value. We can just write, well, the first x, the absolute value of x1 has to be less than or equal to d. The absolute value of x2 is less than or equal to d. Absolute value of x3 is less than or equal to d. And this is true for each of the variables in the decision vector x. Okay, so we're getting closer to representing our infinity norm, right? The infinity norm of the vector x, right? And I'm going to just say this is in dimensions, is less than or equal to d. Now the problem we have that we haven't quite addressed is right here, right? So the absolute value is a nonlinear function. Okay, so how do we linearize it? Well, let's sort of take one of these values and study it a little bit more. So let's say we look at x of I, and we say that has to be less than or equal to d. If we were to put this on a number line, we'd have 0 here, and we would have d and negative d. And what we'd say is that x of I has to be between this region. Well, this looks exactly like a linear constraint. So even though this absolute value is a nonlinear function, it can easily be represented by two linear equations. right? And those linear equations are just given by x of I is less than or equal to d, and then x of I is greater than or equal to negative d. Okay. So what we've done here is we've found a way, for starters, is to say, well, our L infinity norm of our decision vector x can be represented by a set of inequalities that involve the absolute value. And each one of those absolute value inequalities can actually be represented by a set of two linear constraints. All right, this is great news. All right. So now what that means is, again, so I'll write let's say we have some minimize f of x subject to the infinity norm is less than or equal to d. If we were to sort of take this idea and represent it as a series of constraints, we'd first start by saying, well, this is equivalent to saying that the absolute value of x1 is less than or equal to d, the absolute value of x2 is less than or equal to d, right, all the way down to the absolute value of xn is less than or equal to d. And again, I'm not stating it here, but we're going to assume that x is a vector in the real numbers, right? Okay, so these two problems are equivalent. And I just said, well, each of these absolute values can be represented by two linear constraints. So from there, we can say that the problem in the middle, and in fact the problem in the left, is equivalent or the exact same as the following. x1 is less than d, right? And then x1 is greater than or equal to minus d. Now let's make our life a little bit easier and just multiply both sides times -1. So instead of writing this x1 is less than or equal to d, I'm going to write it as minus x1 is less than or equal to, actually, oh gosh, now I'm going to confuse myself. Let's do it up here. So we have xi is less than or equal to d. We're going to multiply this bottom equation times -1. So we get minus xi is less than or equal to d. Okay. All right, so that would be the first equation. And then we'd just repeat this for each of the x. All right, so let's see what happened here. As a little check, if we look at how many constraints we have here, we have 2 times n constraints. All right, not only that, they're all linear, which is great news. All right, so let's take this up a level. In fact, we can even sort these. Why don't we just sort these? So I'm going to go over here. I know it's a little bit messy at this point. But if we were to sort them, and this will become very useful later on, let's say I have x1 is less than or equal to d, x2 is less than or equal to d, all the way to xn is less than or equal to d. So that's some of them, right? So that'd be taking all these equations and sort of ordering them first, right? And now I'm going to take the second set and order them second. Okay. So let's sort of write these second ones. So we'd have minus x1 is less than or equal to d, minus x2 is less than or equal to d, all the way down to minus xn is less than or equal to d. All right, so why does this help us? Right? So one thing that's going to make our life really easy is if we can represent these constraints as a set of linear equations, right? So we always want to get it into the following form. So the question becomes, well, what is A and what is B? Right? So based on this reordering, and of course, well, we know what x is. X is equal to x1, x2, dot, 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 xn. Okay. So what would A and B be? So it ends up that if you sort of look at the structure, right, and you want to sort of work it out, so I'm going to do something like this. So we have our set of linear equations. So our first equation is x1 is less than or equal to d. So our first row is going to look something like this. 1, 0, 0, 0, all the way across 0. All right, we're going to multiply that times our x vector, and that's going to be less than or equal to d. Is there a problem? No problem. Okay. Right. If we now look at our next row right here, we're going to get 0, 1, 0, dot, 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 all the way to 0. And again, that is less than or equal to d. All right, and we're going to repeat this process all the way down to xn. So at this point, we're going to have 0, 0, 0, go all the way across, and we'll have 1. All right. So hopefully this looks like something you recognize. Now we have a bunch more rows, so we have these green guys that we need to deal with, right? And it's going to look pretty similar, right? So instead of 1, though, we're going to have -1. And this pattern is going to repeat all the way down the line. Something like that. And again, the vector on the right-hand side is just going to be filled up with d's, right? And that's where we get all these d's from. Okay. So let's think about what A is then, right? So hopefully you see here, this top part just looks like an identity matrix. And the bottom half of this A matrix just looks like an identity matrix times -1. Right? So what that tells us is that the equivalent, so if we have a constraint such that x infinity is less than or equal to d, well, we can just rewrite that as ax is less than or equal to b, where A is equal to an identity matrix of size n, so I'll just put an n there to indicate the size, stacked on top of minus identity matrix of size n, and B is just going to be a whole bunch of d's, right? And we're going to have 2n d's, okay? So there we go. What we've done is we've taken a nonlinear constraint, right, which is this infinity norm, and we found a way to represent it as a set of linear equations that's equivalent to the original form, okay? So this is not an approximation. This is an exact representation, right? It'll give us the same answer. Yeah. Now, we could certainly take more complicated forms of this constraint, and we can replicate the same idea. So let's say instead of just having the infinity norm, we had something a little bit more complicated, like ax plus b infinity. Actually, maybe I shouldn't use b, but I'm going to. Do I want to be doing that? What I'm gonna do is I'm gonna put a couple tildes over these, okay, just so we can differentiate them from our a's and b's normally. So we're gonna have a tilde x plus b tilde infinity norm is less than or equal to d. So the question is, how do we represent this, and can we use the same ideas that we just learned? Well, you know, for me, I just sort of think about it by breaking apart what's going on inside the infinity norm. Okay, so we just have a matrix multiplication plus an addition. So this is the same idea. If we are to think about the A matrix, well, it's just got a bunch of rows, right? So here, each A tilde corresponds to a row of the A matrix. And we might have m rows, so m is not equal to n, it can be a different number. That gets multiplied times our x vector, which is of dimension n. And then we're going to add in our b. So again, b1 tilde, b2 tilde, all the way to bm tilde. Taking the infinity norm of that, and this is all less than d. Okay. And just to be clear, to call it out, ai tilde is the ith row of a tilde, right, which is coming from here. Okay, so we have some sort of linear operation occurring within this norm. Alrighty. Now, if we were to expand out this multiplication, so here, you know, we again still have the minimize, we haven't changed anything here. And we're going to subject to some constraints. So let's go ahead and sort of do some of this multiplication, right? So the product of this multiplication is going to be a vector. So we're going to have a vector that we're going to take a norm of. All right? So in the first row of that vector, right, we're essentially going to do row times column. Right? And then we're going to add in b1. So we could write that as a1 tilde x plus b1. Right? Next, we'll take our next row, multiply it times x, and add in b tilde 2. Right? And this process is just going to repeat down the m rows. Okay. And we're going to be taking the infinity norm of this guy, and it's still less than or equal to d. Now again, just to be clear here, this is the decision vector x, which is of dimension Rn. Okay. All right. So now that we've done that, we can easily apply what we did before, right? Okay. Nothing's really changed, except now, instead of doing, so if we go back up here, here, we had these absolute values of x1, x2, x3, and we showed how those absolute values could be broken up into a pair of linear constraints. Right? The only distinction now is that instead of just taking the absolute value of xi, we're going to be taking the absolute value of a linear equation for each row. Okay. So what does that mean? Well, sort of skipping ahead a couple steps, that means we can represent this L infinity norm as the following. Okay, so again, whenever you see these double arrows, that means they're completely equivalent. They're the same result. Right. So here we'll have a1 tilde times x plus b1 tilde is less than or equal to d. Right? And then we're going to have the opposite of it, right? So this a1 tilde x plus b1 tilde, well, that's got to be greater than or equal to negative d. Okay. And again, where this comes from, if we just pull out this one constraint, right? So essentially what we're saying is that a1 tilde x plus b1 tilde, we're going to take the absolute value of that, and that's going to be less than or equal to d. And we repeat this process for each row of that vector inside the norm. Okay. So next we're going to have a2x plus b2 tilde is less than or equal to d, a2 tilde x plus b2 tilde is greater than or equal to minus d, and this repeats for all the rows. So again, we're going to have m rows. Alrighty, cool. All right, so again, we can sort of reshuffle things and it will make our life a lot easier. So if we reshuffle them, so I'm just going to focus in on, well, we'll write it, minimize f of x, subject to some constraints. So again, I'm going to take all the less than or equal to d's as one chunk and all the less than or equal to minus d's in another chunk. All right, so these are all the less than or equal to d's. Right. And again, now we have the, we're going to focus on sort of these equations where we have the greater than or equal to minus d. Now, to put it in the sort of standard form or normal form that we're used to, we're going to multiply both sides times -1. So here we have negative ai tilde times x minus b1 tilde is less than or equal to d. And this pattern sort of repeats just like before. Over m constraints.
Excuse me, Professor, for the second equation also should be negative a2 tilde minus b2 tilde.
Yeah, so we're taking this guy, right? So ai tilde x plus bi tilde is greater than or equal to minus d, and we're going to multiply everything times -1. All right, so that gives us ai tilde minus x minus bi tilde less than or equal to d. So that's where that's coming from.
Yes.
Okay. Now, just as before, where we said, well, our equations can be represented as, when we put it in matrix form, we got an identity matrix on top and an identity matrix on the bottom. We get sort of a similar pattern, right? But instead of the identity matrix, in fact, what we end up pulling out is we see all the rows of A multiplying times X, and then we're going to add in all the values of B, right? And then on this bottom half, we have negative 1 times all the rows of A minus all the rows of B, okay? So if we want to find the equivalent matrix equation, so again, we want to put it in the following form: minimize f of x such that ax is less than or equal to b. The question becomes, what is a and what is b here? Well, looking at this, we can sort of pull it out pretty quickly. Right? Now, we do need to do one little trick. This b right here is not a variable, so we're going to have to move it to the other side in both cases. Okay, so that's going to be the one little thing we just have to be careful of. But here, hopefully, it makes sense that our A matrix, this A matrix right here, well, that's just given by A tilde and minus A tilde. Okay, so again, that's what this guy is. This is A tilde, and this guy is minus A tilde. So that will give us the AX part. Right? Now we just need to deal with this B. Well, the B, if we look at what's going on here, it's just equal to D minus B on this top half. Right? And on this bottom half, it's D plus B. Okay. Now, this is sort of an abusive notation because here D is a singular value, right? It's in reals, while B is a vector. Okay. Oh, that should be M. Sorry. Okay. But this is approximately what we're doing. So in this case, the B for the linear equation can be given as follows. So it's going to be D minus B1, D minus B2, all the way down to D minus Bm, right? And all these have tildes. And then that's the first set of equations, right, that correspond to that positive A matrix. And then we're going to have the D plus B's. Okay. So this is how, right? So again, sort of to restate it, if I have some minimization problem where one of my constraints corresponds to AX plus B is less than or equal to D, okay, I can just represent that by a set of linear constraints. AX is less than or equal to B, where that A matrix is a stacking of A tilde and minus A tilde, and a stacking of D minus B tilde and D plus B tilde. Okay, so this is a pretty neat way that we can represent a, whoops, and this shouldn't have an infinity, a more complicated norm in our constraint equations. Okay. So, I think one common question that we get from students is, well, what if we already have a set of linear equations? Right? So what if I were to give you a problem, or you were to encounter something where you already have an, let's say, A1 times X is less than or equal to B1, and now you have an A2X plus B2 is less than or equal to D. how do you handle that? Well, that's pretty easy. You would just have to stack your equations and be a little bit careful, right? So we still want to get it in the form of some general AX is less than or equal to B. How would we do that? Well, in this case, our A matrix would be given by A1, A2, and minus A2. Well, our B just corresponds to our B1. So again, this is a vector. Plus, and I'm going to write this in sort of shorthand, D minus B2, right, which again is this guy, and D plus B2. Okay. So you can just sort of stack these equations up. Right. So that's how we represent an infinity norm using a set of linear constraints. Are we good? Any questions? Stephanie? Yeah? All right, awesome. You guys are like my level, so feel free to, if something doesn't make sense, feel free to please speak up. All right. So the next one we're going to look at is how do we go through a similar process for the L1 constraints. Okay. All right. So we still have some minimization of f of x. But now we're going to add in an L1 constraint. And we're going to say, we're going to take the L1, and that's going to be less than or equal to c. And again, we're going to assume that x is some decision vector of dimension n. Okay. All right, so let's sort of remember what the L1 norm is. Okay, so whenever we take the L1 norm of a vector, it's equal to the sum of the absolute values. Okay. So the trick here is we're actually going to add some decision variables that are representative of this absolute value. So what I'm going to do is I'll say the value, the decision, we're going to introduce a decision variable, T1, that's sort of representative of the absolute value of x1. Okay. Likewise, we're going to have a decision variable T2 that we're going to introduce, T3, all the way to Tn. That's going to represent the absolute value of each of the decision variables. Okay. All righty. So if we were to think about this, what we're trying to do is, instead of saying minimize f of x such that x1 plus x2 dot 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 all the way to xn is less than or equal to c, right? And again, I'm sort of dropping this notation that x is a vector, but please understand that. We're going to rewrite this in a slightly different way. We're going to say, well, because we're going to try to represent each of these absolute values by some t variable, so we're going to augment our decision vector. We're still going to have the x's. But now instead, what we're going to say is, instead of taking the sum of the absolute value of x1, x2, xn, we're actually going to say, let's take the sum of t1 plus t2 plus t3 all the way to tn, and we're going to require that to be less than or equal to c. Now the question becomes, what's the relationship between the x's and the t values? Right? So what's the relationship between xi and ti? Oops. Now, we would like to say something like ti is equal to xi, but we can't do that. So we can't program that in Cplex because this is a nonlinear function, right? But we can do something pretty close. So this we cannot implement. But we can use the trick that we had before when it came to absolute values, okay? Specifically, we can say, well, the absolute value of xi is less than ti. Okay. Why does it, well, I'll sort of step through why this works in a second. But so let's just say we are to represent, instead of using this equality, we're going to use this inequality. Right. This is equivalent to saying, just as before when we bounded xi between d and minus d, right? We did something like that. We're going to do the same idea. But now what we're saying is that xi is between ti and minus ti. Okay? This is sort of the equivalent graphical representation. So we can just write this as xi is less than ti and greater than or equal to minus ti. Okay? This, of course, is just two linear constraints. Xi is less than ti, and xi is less than minus ti. Okay. So we can use this to sort of fill in or explain what each of these t1, t2, t3s are equal to. So here we just add in the constraints. x1 is less than or equal to t1. x2 is less than, and I'm going to group them. First I'll take these guys, and then next I'll take these guys. Okay. So x2 is less than t2, x3 is less than t3, and this goes all the way down to xn is less than tn. Okay. Now similarly, we're going to have all these, again, the negative side of that absolute value. So we'd have something like, oops, and I wrote that the wrong way. Sorry, that should be greater than or equal to minus. Right? So we can multiply this times -1. And we end up with minus x1 is less than or equal to t1. Minus x2 is less than or equal to t2. And this repeats all the way down to minus xn is less than or equal to tn. Okay, so what I'm telling you is that these two formulations, so starting from here, that is equivalent to this guy here. All right. Now, there's one little caveat that sort of needs to be explained, right? Which is, why were we allowed to change what was an equality constraint in the absolute value to an inequality constraint? Okay. And the reason is right here. Okay. This inequality with C is going to drive down or sort of hold back T1, T2, T3, T4. Okay. And in driving that down, it's going to also drive down each of these individual values, right? Which will ensure that each xi, right, the absolute value of each xi is less, the sum of all the absolute values is less than C as well, okay? So it's not a requirement that, again, our goal is not necessarily that, you know, the sum of, let me restate this. We are not trying to say the following. We're not trying to say the one norm is equal to C. We just need to ensure that the one norm is less than or equal to C, okay? And by doing this process where we say, well, T1, T2, T3, all the way to Tn is less than or equal to C, and not only that, that the Ti is greater than or equal to the absolute value of xi, essentially what we're doing, so we can think about it this way, we're saying this. All right, so before we had x1 is less than or equal to c, we're sort of saying the following. Okay, in fact, these are equal, so it doesn't matter. Right? But we said okay, so we're sort of taking this chain where we're saying the sum of the T1s is less than C, but we know these T1s are just greater than or equal to each of these guys, right? Which is then equal to x1. So they end up being equivalent. Okay, so that's sort of the important part here. That's sort of why it works. Okay, so that's cool. All right, so then the question always becomes, well, how do we represent this as an optimization in matrix form? Okay, now we have some added difficulty here in that we introduced some new decision variables. Okay. So before we just had x variables, now we have this combination of x variables along with some new decision variables t. Right. So we're going to want to write in matrix form a minimization. Okay, and now we're going to do it in terms of this decision variable z, such that az is less than or equal to b. Okay, so what the heck is z? Well, z is just a stacking with our original decision variable x on top of the decision variables t. Okay. So if you want to think about that, we have x1, x2, x3, all the way to xn. Okay. And we have a t for each absolute value. Okay, so we're going to have a t1, t2, all the way to tn. All right, so we kind of got our decision variable. Now the next question is, what is A and what is B? Let's go back up. So the issue here is that x1 is a decision variable and t is a decision variable. So if we want to sort of take these, and we're going to want to move all the decision variables to one side. And so the equivalent way we'd write that is if we were to take the ith decision variable, it would be xi minus ti is less than or equal to 0. Again, for the second set, we could do the same thing. But here we'd have minus xi minus ti is less than or equal to 0. Okay. And so again, we have n of these equations for each set. All right, so what does this A matrix then look like? Well, this A matrix is going to have an identity matrix. Actually, let's just write it out. So if we look at the first row, this constraint here, okay, we're going to have something that looks like 1, 0, 0, 0, 0. Okay, so these are n values. Okay, and this is going to correspond to the part of the A matrix that's multiplying times x. Okay, so this x multiplying here. Okay, this part of the same x. Okay, now if we go back to that first equation, we see that we have this ti in it. Okay, but it's minus ti. So here on the equation for the first one, we're going to get minus 1 times 0, 0, 0 all the way over. Okay. So this part of the A matrix is multiplying times the t vector. And again, this is of dimension n. Now this pattern is sort of going to repeat for the second row. The second row corresponds to x2 and t2. All right, so we'll get something like this. And third row, we'll get something similar. And this pattern will repeat all the way down to the nth row. Okay. And so we get this diagonal. All right. So that just corresponds, again, to this first n equations. For the second set of n equations, right here, we're going to have a similar pattern, but now the only distinction is we have a minus in the constraint equation for the x's. Okay. So if we were to draw what these, or write in what these elements are, instead of having positive ones in this matrix, we would have negative ones. And again, this repeats all the way down for n rows. Oops. Now, obviously, there's an easier way to write this, right? And the easier way to just have written this would have been the following matrix: I of size n, negative I of size n, negative I of size n, and then I of size n. Right. So that's our A matrix. Okay, so we've got our A, we know our Z. The only thing we're left with is B. All right, so let's go back up. Right. And again, B is just the right-hand side. And we see in both sets of equations, the right-hand side is just 0. Okay. So what that tells us is that if we sort of go over here, and we want to write down what B is equal to, well, it's going to be 0, 0, 0, dot, 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 0. That's for the first n equations. And then we're going to have 0, 0, 0, dot, 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 all the way to 0 for the next n equations. Right? So if we want to write that in a simpler form, we would just say B is equal to 0. Okay, so a lot of times you'll just see something like that. All right. So it's pretty nice. So again, this is how we could represent the L1 norm. Now, as a homework problem, what I like to give is I sort of ask the question, well, so the typical homework problem, and I think it's going to be on this upcoming assignment, is what if we want to write the following? All right. And we want to translate this into the linear form. Oops, and this is Z. All right. What is A? What is B? And what is Z? Okay. And you're going to want to follow. Okay. So here it's going to be a little bit different because, you have A times each of these values. Okay. So the trick here is you're going to want to replicate the same idea that we did here, right? By saying, hey, what's this calculation? Right? Go through the multiplication for each row. Once you get it for each row, write out the set of linear equations and show how you can sort of pull out what the elements of A are. Okay. Well, it's going to be a very similar idea. So, if you want to hazard a guess, so before, if we, oops, where'd I go? All right, so if we think about the L1 norm, before we had I and negative I stacked on top of each other, and they ended up getting replaced with A and negative A. All right, you can probably guess what's going to happen for the L1 norm. Okay, instead of just multiplying or having 1 times xi, we're going to be multiplying times A. All right, so probably what you're going to see is these are going to get replaced with A and negative A. All right. Some funny stuff might happen to B, right? Because we saw last time D got included into B. So in the same way, this D is going to get included into the B here. Okay. Oh wait, I feel like I missed something. Let's see. I'm missing a constraint, actually. So let's look what happened. So I in that A matrix, I included this guy here and this guy here, but I'm missing one more constraint. No, this guy right here. Oh. Yeah. All right. So we actually need one more constraint. Okay, so I'm gonna, and I even make this mistake in my notes. I think I forgot to add it, and I always forget. So we're gonna add one more row. Okay, that's gonna be 0 all the way across, except when we get to the t's. We want to add up t1 plus t2 plus t3 plus t4 all the way to tn, and we want that to be less than or equal to, I think C, yeah. I want that to be less than or equal to C. Okay. So we should add that in down here. And again, that's just a single row. So the way we can write that is we have a 0 vector, right, which corresponds to this guy. And if you want, if we assume that 0 is a vector, we're going to turn it sideways to make it a row vector. And then we have a whole bunch of 1s right here. Okay. So we can write that as like that. Okay. So if we write this bolded one, so again, just to be explicitly clear, this just corresponds to a whole bunch of 0 values. Well, the 1 vector is just a whole bunch of 1s. Okay. Oh, there we go. And then we need to correct that. There we go. Okay. All right, cool. So let's take a quick break, and we will return at 2:40 p.m. It is 2:36 p.m. right now. So this will just be, well, actually here, let's do 5 minutes. 2:41. All right, so we'll begin in 5 minutes. Okay, that was a little bit longer of a break than expected. Okay. Okay, so the next type of constraint that we're going to talk about are these L2 norms. Now, the good news is we're going to have some relief here. Okay. So what do we mean by an L2 norm? So we have some sort of constraint that's written in the form x, taking the L2 norm of x, is less than or equal to some epsilon. And just as a reminder, this is equivalent to saying minimize f of x such that the square root of the sum of each value squared is less than or equal to epsilon. If we want to, we can take the square of both sides, right? And again, this is still the equivalent problem. So here we'd have x1 squared plus x2 squared, dot, 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 all the way to xn squared is less than or equal to e squared. Okay, so here's the good news. Cplex can actually handle this. So yay. All right, Cplex can do. Okay. So Cplex can actually handle quadratic constraints, right? The only thing we have to be careful of is it has to be a convex quadratic constraint. So in order to ensure that it's convex, we need two things. So we're going to require that it has to be less than or equal to. Okay. And the other thing is that this function here, or this quadratic equation, has to be convex. Okay. So how do we, if we just have x1 squared plus x2 squared plus x3 squared, da, 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 that's going to be convex, okay? So let me maybe do a few steps. So if we had something like x1 squared minus x2 squared is less than or equal to 5 squared, this is not convex. Okay, so this, I don't know how you guys, I'm going to try to draw this as best I can. This sort of looks like a saddle, like, oh gosh, that's a terrible drawing. Let's see, saddle point. Is it called saddle point? Yeah. Oops, there we go. Escape. Share. So we just have to be careful because if we start having negative x squareds or something like that, it's going to look like this, right? And so while it might be convex in one dimension, right? So it's bowl-shaped in one, bowl-shaped up in one dimension, it's bowl-shaped down in the other dimension, okay? And because of that, it's not a convex set. And so we always need to be careful about that. So this is bad, all right? So we don't want, let me hide this. You don't want anything like this, okay? Even then, you might think, well, if we have all pluses, well, it's not strictly a rule that if you have a minus sign, it's not convex, right? So the way that you want to think about it is any quadratic equation it can be represented by X transpose A times X. Right? So there's something we discussed previously in lecture, I believe. And we know that a quadratic is convex. How do you spell? Oh gosh, I'm a terrible speller. Quadratic. So we know this quadratic is convex if the eigenvalues of A are all greater than or equal to 0. Okay, so what do we mean by that? So again, if you have this A matrix, you know, we can use Octave Online. I'm just going to okay, so let's say we had an A matrix 2, 0, 0, 2. This one's pretty simple, but if we were to take the eigenvalues of A, we just get 2 and 2. Okay, so this would be a convex function. But you could have a different A matrix that was like 2, 1, 1, 2. Okay, and we could say, well, what are the eigenvalues of that? In this case, the eigenvalues are 1 and 3, so this would still be a convex function. So let's go ahead and do that as a quick example. So let's say A was equal to 2, 1, 1, 2. All right, so if we were to do X transpose A times X, let's see, what would we get? So again, we're multiplying x1, x2. This is just a two-dimensional case, but it could be in any number of dimensions. Sorry, I'm just sort of writing this very quickly. I know it's messy. So here we would have 2x1 plus x2, and then x1 plus 2x2. Oops, and that should be row times column. Sorry, let me write that again. So 2x1 plus x2, right? So that's the first part of the vector. Then we have x1 plus 2x2, and that gets multiplied times x1, x2. Okay, so if we do that multiplication, we get 2x1 squared plus x1, x2. Is that right? Yeah. Okay, sorry. And then what do we have next? x1, x2. So here, this guy times that guy. So that was the first one. And now we're doing these elements. So x1, x2 plus 2x2 squared. Okay, so that sort of simplifies down to 2x1 squared plus 2x1, x2 plus 2x2 squared. Okay, so this would be a convex quadratic. We could certainly play, you know, again, you sort of have to be careful. It's sort of deceptive. So let's see, you know, if we have something like that, I don't know if that's, yeah, so now we have a negative eigenvalue. Okay, so this would begin to look like a saddle point or some other weird conic. Okay, so we just have to be careful about that. Now the relief is, so, geez, overheating. Okay, so as long as you can, as long as your quadratic is convex, you're okay to type it into Cplex. So literally, in Cplex, I could write, so let's say we have some maximize, you know, 5x1 plus 3x2, subject to, and if you're to literally write in your constraint, how do you do multiplication in Cplex? You have to do the little asterisk, right? Yeah, so let me literally write this how I'd write this. Okay. So, oh, and actually, I'll probably have a video on how do you write a squared, all right, in Cplex. I suspect, I don't remember if it's, I don't think you write it like that, like up hat 2. For some reason, I think it's something weird. It might be like this. Okay, I don't know. I'll follow up on the video. But if you're to write this into Cplex, let's say less than or equal to 5, this would actually work. So Cplex can handle a quadratic constraint like that. Okay. So that's good news. Towards that end, certainly, if you have a more complicated constraint like ax tilde plus b tilde norm is less than or equal to e, this will always be convex. Okay, so here you don't have to worry about it. That's the really nice part. Okay, if that A matrix is inside of the norm, it will preserve convexity. And this is something we had learned earlier, right? This is one of the properties of convex functions, okay? That, if you guys remember, I think we said something like, if we have some constraint function g of x is less than 5, and we apply a linear transform, right? If g of x is convex, then g of some linear transform is also convex. So that's sort of where this is coming from, okay? And we know that L2 norm is convex, okay? So if we just multiply ax plus b inside of the L2 norm, it's still convex. So that's really good news. And again, we would just sort of, you would transform this in the same way. So we would talk about, we would take the square of both sides. And it gets a little bit more complicated, but effectively what this becomes, you have to sort of work out the, the multiplication and the addition, which gets very messy, but it can be done, okay? If we were to just do this part becomes like this, okay? And the nice part is, okay, but we're also going to have other parts that come from the multiplication of b and stuff like this. So, but either way, all you need to know is that this L2 norm is convex, and when you put in ax plus b, that remains convex, but you got to have to work out the steps, all right? So what do I mean by work out the steps? Actually, I can kind of do some of them here. Why not? So you do the same thing, right? Where you say row 1, row 2, all the way to row m is multiplied times x plus b1, b2, all the way to bm. We're going to take the square of that, and that's less than or equal to e squared. Okay, so the L, yes?
When you put hyphen, you mean it's a diagonal matrix?
It's this guy right here. Wait, which hyphen? Oh, no, this.
Yeah.
Oh, sorry, no, that's just indicating it's a visual indicator that it's a row. Yeah, sorry, that's, for me, this is my little trick, because sometimes I'm not sure whether we're talking about a vector that's up, down, or a vector that's sideways. So this is my own personal notation. Nobody else does it. I just do it as a visual indicator that each of these are row vectors. Okay? Yeah. So if we want to translate this, right, we know, again, that the absolute value, or sorry, the L2 norm squared is just equal to x1 squared plus x2 squared plus dot, 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 xn squared. Okay? So if we're going to take the L2 norm of ax plus b and then square it, that's the same thing as saying a1 tilde times x plus b1 squared plus a2 tilde x plus b2 squared plus, and again, we just sort of repeat this process. right? And all this is less than e squared. Okay, so the problem is we have to go through and do all these multiplications, which gets really messy, but it can be done, okay? The idea is it can be done, but it just gets messy. And then in the end, it looks something like this, right? It's some quadratic constraint that we can write out. Maybe if I find a nice little way of representing it, I'll sort of post something. Well, I guess we could kind of do some of it, right? So this would be a1 tilde x plus b1 tilde, and again, oh gosh, this is going to be messy. All right, so let's just focus in on this guy. So here we could do the distribution, right? So you'd get something like that, right? Another way that we could write this is x transpose times a1 tilde transpose times a1 times x, right? Here we would get 2 times a1 tilde x, and we'll get a b1 somewhere there. Oh. I think I might have put the tilde in the wrong place. Row times column plus b1 squared. Okay, so if you sort of repeat this process for every value, right, you end up being able to write it as x tilde a times x plus probably something like 2 I don't know where the b goes, but we're going to pretend it's something like that. I feel like I might be getting that wrong. Ax times, well, we'll keep it this way. I feel this is wrong, right? So I'm just going to be brutally honest. Plus b transpose b is less than or equal to e squared. Okay, so I'll sort of verify this. I have some questions about that part, and this should be a tilde, 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 tilde. Okay. But again, we can find a representation. It's just multiplying it all out. The good part is, as I said, I think we went over this in lecture at some point, but if you ever take a tilde, or you take a matrix and you multiply it times itself, or multiply it times transpose, this is always convex. Okay. So this vector or matrix that results from A transpose A, always convex. It's something called positive semi-definite. Okay. This is just a linear function. Okay. It's not an x squared, it's just A times x. So this is linear, so it's convex, right? And this is just a constant. Okay. So this whole thing is convex, right? But we already knew that. But anyways, okay. Let's see. 4. All right. Those are all the major convex sets that you might ever encounter, right? There are other ones, but these are the big ones. These are the big 3. From here, what we want to move on to is how do we translate cost functions into LPs? So again, before we are looking at, we're sort of looking at the following, right? Where we are trying to understand how do we represent these constraint equations as convex, linear constraints. Now we're going to instead focus on the cost equation, right? So what if this guy is a nonlinear function? And we're going to sort of ignore the constraints for now. So I'm just going to write it as x is in some constraint set. Okay. And our goal is we want to end up representing our problem as a linear cost equation plus maybe a quadratic. So somehow we're going to want to represent any nonlinear function as a linear function with a quadratic. So it might have the quadratic, it might not. Okay. And the reason why we're allowing for this quadratic, again, is because Cplex can handle quadratic equations, okay, as long as they're convex. Okay, so let's sort of work through, we're going to work through a couple simple cases that come up fairly often. So the first one is, well, what if our cost equation is the L1 norm? Okay, so we're going to sort of repeat the same process we did with the constraints, but now we're going to ask ourselves, well, what happens if we have an L1 norm in the objective function, or an L infinity norm, or even a quadratic? Okay. Alrighty. So again, here in this particular problem, we're saying let's minimize the L1 norm of x subject to x being in some constraint set. And we're going to want to find a linear representation of this. Now we're going to use the same tricks that we did before, right? So again, this L1 norm is equal to the absolute value of each of the components. And so the trick that we're going to do here, just like before, we're going to introduce new decision variables that correspond to the absolute value of each of the components. Right? So instead of saying let's minimize the L1 norm of x, we're going to say let's minimize t1 plus t2 plus t3 all the way to tn. Right? But now we need to define what t1, t2, t3, tn is equal to. And so we're going to use the same trick as before, where we say, well, any ti is less than or equal to xi. Right? And so this just gets represented by saying xi is less than ti and greater than minus ti, which again is just two constraints. Is it a minus, I think? Yeah. That should do it. Okay, and again, we're going to want to move all our, when we add in these decision variables, usually we're going to want to put all the decision variables on one side. Okay, so this is just xi minus ti less than or equal to 0. and minus xi minus ti is less than or equal to 0. Okay, so using the same trick, this L1 norm is just equal to the following, right? So we have minimize t1 plus t2 plus t3 all the way to tn, and we have to relate our decision variables x1, x2, x3, x4 to all the t's, right? So we just sort of write them in one at a time. So we'd have x1 minus t1 is less than or equal to 0. x2 minus t2 is less than or equal to 0. All right, and this is going to repeat for all of the xn and tn. All right, and then we're going to have the negative ones, right? Okay. So this is an equivalent representation of saying, let's minimize the L1 norm of x. So the problem just now becomes, well, what is this representation when we put it into matrix form? Okay, so now I'm using z in order to represent the idea that we've augmented our decision variables. Okay. All right. So just as before, our z is going to be a combination of our old decision variables x with these new decision variables t. Let's start by thinking about what is c. Okay. So c, if we go back up top, what we want to do is we want c to represent the adding up of t1, t2, t3, t4, and so on. Okay. So in that case, C transpose is going to be a whole bunch of zeros followed by a whole bunch of ones. Okay. So these zeros are multiplying times all the x values, while these ones are multiplying by all the t's. Right? So that's how we get t1 plus t2 plus t3 plus t4, and so on. Okay, so we got C, we have Z. Now we need to deal with A. And A looks like what we had before, right? We see it broken up into two different groups, right? This looks something like the identity matrix times X minus the identity matrix times T. And here we have minus the identity matrix times X minus the identity matrix times T. And this is all less than or equal to 0. Okay. So that gives us a pretty good idea of what A is equal to. So A is going to be equal to the identity matrix of size n minus the identity matrix n, and then we have minus I and minus I. Okay, and our B, oops, is just going to be 0. Okay, and here, just remember, for this particular case, it's 2n, because you're going to have a whole bunch of zeros for the first set of equations, the first block, and then a whole bunch of zeros for the second block. Okay, so we have a block of 2n zeros. Okay, that's pretty good. You could sometimes people formulate this a slightly different way, which is perfectly acceptable. Another way that you could formulate this, right, and this is all depending on how you want to do it, you could formulate it as minimize t sum subject to all your constraints that you had before. So I'm going to copy these guys. Okay, but we just have to define what T sum is equal to. So we would say T sum is equal to T1 plus T2 plus T3 all the way to Tn. Okay, and again, you could find the equivalent representation. So if you were to do something like this, then here your Z would be equal to your X, your T's, and then finally you'd have a T sum. Right? So if you want to think about this, Z would be in the dimensions of 2n plus 1. So that one extra variable is the sum. All right. Your A would be pretty similar. So you'd still have the i's. But now you would have to deal with this extra constraint. And actually, we need to put some zeros here. Okay. So again, this block corresponds to multiplying times the x. This block corresponds to multiplying times t. Well, this single column corresponds to multiplying times t sum. Okay. And so in this case, we're going to add one extra row. And again, that's one equation, just one row. It's not a block necessarily. And so what we're going to have is something that looks like 0, a vector of 1s, which correspond to these guys. Right? And then we're going to have a single value of negative, well, I guess you could do -1. How do we want to do this? So we want to put all these t's onto the other side, right? So in this case, I'm saying that t1 plus t2 all the way to tn minus t sum is equal to 0. So these are equivalent statements here, okay? And so that's how we get this minus, is how we get a -1 there. Okay, and again, our b, in this case, we're going to have a 0 block for here, a 0 block for here, and then we have a lone 0 right there. Okay. In the case for the c vector, it's going to be 0 times all the x's, 0 times all the t's, but we're just going to multiply times 1 times t sum. Okay. So this is another way we can formulate it. It's more or less the same formulation. We're just adding another decision variable to make the problem a little bit more readable. So not much has changed. Okay. Again, you can sort of replicate the same process. If you want something like minimize ax plus b L1, you could certainly do that. You just have to work through all the math, right? And again, probably what's going to end up changing are these values in here, right? For the most part. So instead of multiplying x times I and -I, we're going to multiply it times a and -a. And probably what will change, because you added in this b vector, oops, sorry, let me put tilde, b tilde, this is probably going to change over here. There's going to be some adjustments and moving around. Okay. Okay, so we have an idea of how to do that. Okay, so here it's just sort of this process of repeating the same steps, right? But things sort of, they work out more or less similar to how we saw them in the constraints, but a little bit different. So at this point, we can talk about, well, how do we minimize the infinity norm of x subject to some additional constraints. Okay. So again, remember the infinity norm is the maximum of the absolute value of each component. again, we have sort of a similar trick. So let's sort of recall what we did for the L infinity norm constraint. Okay. So for the infinity norm constraint, let's see, we had the infinity norm of x is less than or equal to d. What we end up doing is rewriting that as a bunch of constraints where we have x1 is less than or equal to d, x2 is less than or equal to d, and so forth and so on. And then we have a minus block. Okay, so we're going to sort of repeat the same process, but d is going to be a little bit different. Okay. Let's see. In our case, what we're going to do is we're going to introduce a new variable that represents this maximum. So we'll call this Tmax. Okay, so Tmax, what we're going to say is Tmax is greater than or equal to the maximum of the L infinity norm. Okay. Now let's think about this. If we minimize Tmax, that means we're squeezing down the L infinity norm. So we're equivalently minimizing the L infinity norm. Okay. All right. So the way we end up writing this is we say, let's minimize Tmax subject to whatever constraints we had before, right? But now we're going to introduce some new constraints. So we're going to say, well, the absolute value of x1 has to be less than or equal to Tmax. The absolute value of x2 has to be less than or equal to Tmax, right? All the way down to the absolute value of xn has to be less than or equal to Tmax. Now again, we can use the same sort of trick where we convert these absolute values into two separate linear equations. Right? So again, these are all equivalent to each other. So we would have x1 is less than or equal to Tmax, x2 is less than or equal to Tmax. This goes down all the way to xn is less than or equal to Tmax. Right? And then we're going to have the negative of that absolute value. So that's minus x1 is less than or equal to Tmax. Minus x2 is less than or equal to Tmax. Does that work out? This always confuses me. So again, that's just coming from this equation here. So we've listed that side, and then we have to deal with this side. Yes, so that is correct. All right, so this repeats down for all xn. Okay. So again, this is the equivalent problem, but now it's a linear program. Okay. So let's think about this. We want to convert it to a minimize C transpose Z subject to some AZ is less than or equal to B. Okay. So how do we do this? Well, our Z vector of decision variables is just X. Okay. But all we had to do here is we introduced only one variable, which is this Tmax. So what that means is Z is of size n plus 1. So we're only adding in one decision variable. Right? Let's do C. Our C, well, if we look at what's happening, right? in this equation, we don't have any x values here, x1, x2, x3, x4. All we have is t max. Right? So our c will look something like 0, 0, 0, 0, and then finally the value 1. Okay. In terms of A, what do we get? So if we look at this block, right, we can move the T maxes over. It looks something like the identity matrix times X minus the identity matrix, oh, not even minus the identity. Oh yeah, minus the identity, how do we write this? I'm going to write this in a little bit weird way. So we're going to multiply times T, or not multiply, subtract a vector of T maxes. Okay. And the way you'd actually write that is 1 times T max, right? Where 1 is a vector. Okay. So that's actually the appropriate way to write it. Down here, we would have minus Ix minus 1 vector times T max. Okay. And again, this is all less than or equal to a vector 0. Okay. So that gives us some indication of what we need in our A matrix. So our A matrix is going to be I times a bunch of 1s, a column of 1s, and minus I times a column of 1s, and I think we have a minus sign there. Yep. Okay, so again, this corresponds to T max. This block corresponds to X, and B is just going to be a bunch of zeros. So there we go. So that's how we would write our, in matrix form, the L infinity. Okay, so what you'll see me do in the videos is I'll do an example of actually doing this, right? So I think here we're just seeing this as like, oh, a bunch of matrix equations, but how do we actually do this in Cplex? And there's a variety of ways of doing this. So one of the ways we'll show you is you can make these matrices in Excel or something like that and then have Cplex read it in. Unfortunately for the people who have Macintoshes, the Mac version of Cplex cannot read in Excel files. Okay, so I don't know what to tell you guys. Get a Windows machine if you can. Okay? Yeah, yeah. So, yeah, I don't understand why that's the case. I feel like reading in a text file should work no matter what operating system you're using. But for some reason, at least in the last version of Cplex, Macintoshes had issues. So we'll sort of figure that out. Okay. So the next sort of one that we want to look at is an L2 cost objective function. Okay. So again, we sort of looked at this idea of, well, if you have a L1 in your objective function, how do we convert that to linear LP? If we have an L infinity, how do we do a LP of that? Now, again, you know, this, so let's say we have something like that. All right, so the trick here is to realize that minimizing and I'll sort of put this broadly as minimizing AX plus B to norm, right, is the same as minimizing ax plus b 2 norm squared. Okay? So the optimal solution for this top problem is in fact the optimal solution for the bottom problem. Okay? So let's start with that. All right, so this is some good news, right? So that means minimizing the L2 norm squared, subject to the same constraints, gives us the same answer. Well, minimizing the L2 norm squared, well, that's just the same thing as saying, let's minimize x1 squared plus x2 squared plus x3 squared, and so on. Okay? This here is a quadratic equation which Cplex can handle. Okay? So that's good news. Now, we do have to be a little bit careful. Okay? So even though I told you that these two problems, if we optimize these two problems, they will give us the same solutions. That is not the same thing as saying minimizing C transpose X plus K times the L2 norm that these are equivalent to okay, these are not the same thing. Okay. Yeah, because here we're squaring the L2 norm, but we're not squaring the whole function, right? So it'd be the same thing as saying like 5 plus 3 is not equal to the same thing as 5 plus 3 squared, right? Even so, it's also 5 plus 3 squared is not equal to 5 squared plus 3 squared, right? That's also, right? What is this? 64, 25 plus 9, right? These things aren't equal. So it sort of affects how the solution ends up, right? So it's not just that they're not equal, but they're not scaling at the same rates, right? So because you don't, this becomes way more important than the first term, okay? And so you're going to sort of shift what's important in your optimization. So these two are not equivalent formulations. This happens quite a bit in optimization problems where you want to have a linear part plus the norm of your vector. This is very common. So you just have to be careful and realize that they're not equal, okay? But this is equal, right? If you're squaring the whole quantity on top, then you're okay. Right? And so that's what we're doing here. Here, what we do is we take this whole thing and we square it. And minimizing the square of the whole thing will preserve the solution. Okay, how much time do we have? Okay. What time does the lecture end? 14. Okay. Alrighty. We're gonna stop here for now, okay? Because this next block that I want to lecture on is certainly going to take an hour and a half to 2 hours, okay? But it's very important that I cover it this week. So instead of recording the lecture and then stopping halfway and then doing it next week, what I'm going to do is record a whole lecture on this and post it, okay? So let's do that. That way, yeah, this is too important to interrupt. So I need you guys to see it in one continuous step. Okay, so with that, we're gonna end lecture. And I will post a video this weekend. Stephanie, can I make you responsible for like sending me a message if you don't see today's lecture posted and if you don't see the part 2 posted Sunday? Yeah, okay? All right, cool. And actually, one more favor. Homework. I gotta post homework tomorrow. Okay? Yeah, so tomorrow, if you don't see this lecture, what we talked about today posted,
Tomorrow night.
Tomorrow, first thing in the morning, or whenever. Yeah,
Okay.
yeah,
I'll try, okay.
yeah, yeah.
I'll remember.
Because it's hard for me because I know you guys don't know this in my personal life. I fly directly after this lecture to DC. And so sometimes it's like the video, it takes a while to process and then it takes a while to upload. And then even when I do that, sometimes it doesn't publish on web courses. I have to actively press publish, even though I post it. So, and I really want people to get this. I want to try to do a lot better. So yeah, if you could just do me the favor of, if you don't, yeah, tomorrow morning, just send me a quick message. Did you post everything you're supposed to post? Okay?
Everything. So
Yeah.
tomorrow morning, everything.
Yeah, just say, did you post your stuff? And then Sunday, if I didn't post the extra video, then whip a noodle at me or something like it. Yeah, okay? So we'll be good. Okay, guys, that's it for today. Again, I should have exams graded by the end of next week. I was looking through a few of them and you guys did pretty well. If there are any major issues, I'll touch base with you. Again, I think, my goal is for everybody to do well in this class, right? I think the exam was relatively fair. Maybe the last problem was a little bit tricky, but, again, that was extra credit. And we're gonna, again, I think we'll have one more lecture that's live, and everything else will be like Cplex and getting ready for your project and stuff like that. And we'll go from there. All right, if there are any questions, feel free to ask them now, or else.
Excuse me,
we'll hang up. Yes.
Is this homework separate from the project or part of it?
Yeah. So that we still have a
Okay.
couple of homeworks. So
Okay.
the homeworks will assist in helping you do this project.
Okay.
Yeah. So that way you just don't like jump into doing something really hard.
Okay.
It's like an interim step. So you can address one issue one modeling aspect at a time.
One is that. Thank you, Professor.
Okay, no problem. All right, guys. I'll see you later. Have a good one.